In part A, we determine the exact value of R. So let's see how to determine the value of R using this population model. P of t equals P naught e raised to the power of RT, where P of t is the bacteria count after t hours. P naught is the initial population, that is the initial count of bacteria. R represents the relative growth rate, and t is the time in hours. So let's use the given information to determine the value of R. We are given that initial size of the bacteria is 1000, and this means P naught equals 1000. And we're also given that after 1 hour, that is when t equal to 1, the bacteria count is 8000, that is P of t equals 8000, or otherwise this equals P of 1 equals 8000. So I'm going to plug in t equal to 1 into this population model. So therefore we get p of 1, and this equals, let me also put p naught as 1000. This is 1000 e raised to the power of r times of, replace t by 1. So therefore this becomes r times of 1. Now we know that P of 1, which is the population after 1 hour, is 8000. So replace P of 1 by 8000. And so this becomes 8000 equals 1000 times e raised to the power of r times of 1 is r. Now we divide both sides by 1000 and this side by 1000. So we get this thousands cancel, and 8000 divided by 1000 is exactly 8. And so we get 8 divided by 1, which is 8. This is 8 equals, on the right side we have e raised to the power of r. And to determine the value of r, we take natural logarithm on both sides, that is natural logarithm of 8, and this equals natural logarithm of e raised to the power of r. Now using the power rule, we can put this r in front. So therefore we can write natural logarithm of 8, and this equals r times of natural logarithm of e. We know that natural logarithm of e is equal to 1. So therefore we can say that this is 1, and r times of 1 equals 1 r. So therefore we get natural logarithm of 8 equals r. And so this is the exact value of r, which is natural logarithm of 8. We now answer part B. Here we have to determine the time it takes for the population to reach 15,000. So first let's write the population equation. We have P of t, and this equals P naught is 1000, and e raised to the power of, we can replace r by natural logarithm of 8. So it becomes natural logarithm of 8 times of t. And now we are going to plug in P of t equal to 15,000 into this population function. So therefore this becomes 15,000, and this equals 1000 times e raised to the power of natural logarithm of 8 times t. And so we have to determine the corresponding t by solving this equation. First I divide both sides by 1000. I cancel this 1000 with this 1000, and 15,000 divided by 1000 is 15. So we have 15 on the left side, and this equals e raised to the power of natural logarithm of 8 times of t. Now once again we apply natural logarithm to both sides so that we can solve for t. So here we have natural logarithm of 15, and this equals natural logarithm of e raised to the power of natural logarithm of 8 times t. And once again, if we use the power rule, this complete power expression will be put into the first. So in the next step, I can rewrite this as natural logarithm of 15, and this equals natural logarithm of 8 times t times natural logarithm of e. We know that natural logarithm of e is 1, so we can simply ignore this one, or I will just remove this from the equation. So We now have a natural logarithm of 15 equals natural logarithm of 8 times of t. So to solve for t, we should divide by this natural logarithm of 8 to both sides. And rearranging for t, we get t equals natural logarithm of 15 over natural logarithm of 8. So we can put this expression into the calculator, and when we do that, we get approximately 1.3, and this is rounded to nearest tenth of an hour. So this is rounded to nearest tenth of an hour. And so we see that it takes 1.3 rounded to nearest tenth of an hour. It takes 1.3 hours for the population to reach 15,000. And so this answers part B question.